exciting part. So in general chemistry, usually, I remember I went to high school here in the United States, 9th grade, biology. Yeah. Or no, I think it was general science, they called it. 10th grade, biology. 11th grade, I took chemistry. And I was taught about this. 12th grade, it was physics. Right? So you take physics last. I guess because you have to build up knowing some trigonometry to be able to, some math, to be able to do some physics. But I remember seeing this expression, right, during chemistry class. I didn't like chemistry when I was a high school student. I didn't really have a very good chemistry teacher. I think it was a biologist who had taken chemistry, and therefore he was teaching chemistry because he had taken chemistry, not because he, but anyway, it was confusing, and so I didn't develop a passion for chemistry. And so when I went to college and I went in as a physics major. As a physics major, we had to take 1 year of general chemistry. Guess when I took it? In my senior year, at the end. It's like, at the end. And then we were told about this. But by then I had done all of these calculations in my more advanced physics courses, right? So you take chemistry without having taken physics, and of course this is chemistry, right? But I hope that you can see what's going on over here to get to that result. What did I use? I used, that's an expression for energy, right? You learn about energy you learn about energy in chemistry, but in physics, kinetic energy, potential energies, right? You learn about potential energy in a spring, that's stretched or compressed, gravitational potential energy. In this case, you want the electrical potential energy, which you learn in electromagnetism, right? So this is 1/2 mv squared. This comes from classical mechanics, and electrical potential energy comes from classical electrodynamics, right? So you put those two together and you get this. Now, what else did we do? Well, a very key step in obtaining that result was writing something about orbital angular momentum. That's physics. That's mechanics. Right? You learn about this in classical mechanics in Phys 185. So MVR, and then this was just something that he guessed and turned out to be a good guess. And then that's another idea over there, right? That comes from orbital angular momentum, which has to do with classical mechanics. And then to get this expression for the speed, which I plugged in here, right, for the orbital angular momentum expression, I had to use F equals ma, which is classical mechanics, right? Newton. So it's really, all of this is really physics leading to this result, right? Except that because usually students haven't had physics by the time they take chemistry, they just take you straight to that expression, okay? But then a lot of steps are left out, right? So I would like to focus on this expression and this other expression, because once you know a couple of numbers, it's easy to figure out the other numbers. So for example, I never really bother, I remember it, but anyway, that expression for the orbits, according to Niels Bohr, right? So we have that Rn is 0.53 angstroms times n squared, right? Well, we can make a little table, right? We can make a little table. If n is 1, then R1, this is called the first Bohr orbit. That will be when R is the smallest, right? So it's called 0.53 angstroms times 1 squared, which is just that, right? Well, what if n equals 2? Well, the second allowed orbit, it's 0.53 angstroms times, 2 squared times 4. I don't know that number. Those are the numbers that I don't know. If n equals 3, but whatever it is, it'll be the first Bohr orbit multiplied by 4. The next one is going to be the first Bohr orbit multiplied by 9, because 3 squared would be 9. The next Bohr orbit is going to be 0.53 angstroms multiplied by 16, and then multiplied by 25, and then multiplied by 36, and multiplied by 49. You get the point, right? So, I don't know what the numbers are, but I know how to get them if you give me a calculator. And times 9 plus 3 squared, right? And then, so this is 0.53 angstroms. Nowadays, people like to use nanometers instead of angstroms, but you know, times 16, and blah, 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 blah. So many angstroms, right? The point is that the second allowed orbit is 4 times as large for the radius of it than the first one. This other allowed orbit is 9 times as large as the first one. The next one is 16 times as large as the next one. Then 25 times as large, 36 times as large, 47 times as large. So that's that. These are the numbers that I just don't remember. Now, for the energy levels, I do remember a few of them, and we can double check since you have the calculators. Now let's talk about the energy levels. So the energy would be minus 13.6 electrovolts over n squared, right? Well, if n is equal to 1, this will be E1 equals minus 13.6 electrovolts divided by 1. So that's it, right? Electrovolts. If n is equal to 2, then this should be minus 13.6 electrovolts divided by 4. And I think that's minus 3.4, right? Electrovolts. And then if n is equal to 3, then E3 is minus 13.6 divided by 9, and that should be minus 1.51, I think. If n is equal to 4, then E4 is minus 13.6 divided by 16 electrovolts, and that should be minus 0.85, I think. And the other one is minus 0.5 something, so it just goes like that. Now, which of these energy levels is the lowest? So I'm going to erase this derivation here. So which is the lowest energy level?
The first.
Which one?
N equals 1.
N equals?
1.
Or what would happen if n equals infinity? It would be minus 13.6 electrovolts divided by infinity, and that would be 0. So which of all those energies is the largest one? Let me ask you the question backwards. The largest one. Which energy value is the largest one? Minus 13.6 or 0? Which is larger? Minus 13.6 or 0? Remember that number line? So what's the answer? Which is the largest one? 0. Right? Minus 13.6 is more to the left in the number line. So pretty much there are a couple of ways that we can think of this. If I draw an energy level diagram and I go like this, well, this is energy. And suppose this is the lowest energy level, right? That would be the one, that's the lowest one, minus 13.6. This would be n equals 1. And that energy, E1, will be minus 13.6 electron volts. Now, if I consider n equals 2, it's actually higher in energy, right? So this is in electron volts like this, right? But I'll put the units over there. So then this would be E2, and this would be minus 3.4 electron volts. It's a higher energy than minus 13.6. If I do n equals 3, and I'm kind of spacing them equally, but they're never equally spaced because you have this 1 over n squared downstairs. It's just that, just so that we can see it here. So this is E3, that's minus 1.51, I believe. If not, check me. I'm gonna draw n equals 4. And then this E4 is minus, what is it, 0.85? Somehow that rings a bell. And then tum tum tum, and then you get to n equals infinity. And the energy there is 0. Okay? Now, above that, you have, positive energies, right? And so what I want you to realize is this, okay? This is discussed in Physics 185. If you consider two objects interacting with a force that drops as 1 over r squared, like the gravitational force, m1, m2, separated by a distance r, there's a force of gravity, right? That force of gravity is capital G, m1, m2 over r squared. So that meets that criterion. And if you consider the electrical force, one charge, another charge, separated by a distance r, right? If this is plus and that's minus, then they will attract. And if they're both positive or both negative, they'll repel. But the magnitude of that force, right, is Coulomb's constant, Q1, Q2, regardless of whether it's plus or minus, but it's 1 over r squared. So with this force, there is a potential energy called gravitational potential energy associated with the gravitational force. With this other force, there's a potential energy associated with that force is called the electrical potential energy. Both of these forces are said to be conservative forces. And if you write an expression for the energy, the total energy, that would be the kinetic energy plus the potential energy, whether it's gravitational or electrical potential energy. The result is that if the energy is negative, then one object is going to orbit around the other one in an elliptical path. And an elliptical orbit is a closed orbit. It's a bound system. If the energy turns out to be 0, then the path of one object in the vicinity of the other one as they interact with this force that drops as 1 over r squared, it's a parabolic path. Parabolic orbit. But a parabola, if this is the vertex and you have a parabola, right? That's a point over there. The parabola just comes in one. It doesn't close. It doesn't repeat itself. So this is an unbound orbit. And if the total energy turns out to be positive between, these objects, the orbit of one in the vicinity of the other one is hyperbolic. Which is also an open orbit, which is unbound, or open. But the one that's bound is a closed one. Right? So, the total energy, right, can be this. So, if the electron is bound to orbit around the nucleus of the atom, making up a neutral hydrogen atom, then the energy has to be, the only possibility for the closed orbit so that it repeats and repeats and repeats and keeps going around, it's an elliptical orbit and it will be a bound system, so the energy has to be negative. And that's what we get over here. Right? The energy is negative if it's a bound system. So if the energy of the electron is any one of these values over here, except for the 0, up to very close to that, right? Two things. One, the electron is bound to orbit around the nucleus, around the proton. And 2, the energy can only be this value, or this value, or that value, or that value, but nothing in between. So the energy levels are said to be quantized. it's this or that, but nothing in between, or that, nothing in between. It's discrete. This, as opposed to being continuous. So then you have quantized energy levels. First of all, you have a bound system. With quantized energy levels. Right? And this is true also of a mechanical system. I mean, very quickly we can do that, right? If this, for example, is the Earth, and this is the moon, or some satellite, right? And you consider the motion around it, right? VR, the force of gravity, is that, right? And so you do F perpendicular equals MA, on the centripetal axis, then this would be G, M of the Earth, M of the moon, let's call it M prime, over R squared equals M prime, that's the thing that's moving, V squared over R, and here you get that M prime V squared is capital G, mass of the Earth, mass of the moon divided by R, right? And if I divide by 2 on both sides, this is the kinetic energy term, right? And so the total energy would be the kinetic energy plus the gravitational potential energy. So this is 1/2 mv squared plus, and then this minus capital G, mass of the Earth, mass of the moon divided by R. That's an energy, so it's 1/R. The force is 1/R squared. And then, it's basically what we did before. Now I take this kinetic energy term, and instead of using 1/2 mv squared, I'm going to use this, plug it in here. So you get capital G, mass of the Earth, mass of the moon, or whatever, over 2R minus capital G, mass of the Earth, mass of the moon over R. And you get that the energy is minus capital G, mass of the Earth, M prime over 2R. This is the expression that I had previously that I erased for the case of the electron going around the proton, except that the G got replaced by Coulomb's constant, this got replaced by the charge of the proton, and this got replaced by the charge of the electron. But you had a minus sign and a 2R. Point is that it's negative, so it's bound. Okay? So it's general. So if an electron is interacting with a proton and the energy of the electron is negative, then it's bound to go around the proton. It's a bound system. And if it's doing that, the energy of the electron cannot just be any value. It has to be only certain specific values. And these are the values. Now, what happens in the case of gravity? Suppose I ask this question, and usually we answer this question in Physics 185. We say, what if I take these keys, right? And the keys have a mass, like M prime. And here's the Earth. And I want to throw these keys upwards. And I want them to never come back. I want them to escape from the Earth. So, well, there's a minimum speed that I need to throw them at, called the escape speed from the Earth. And if I throw it so that the keys move faster than that, they'll definitely never come back. So what is that minimum speed? What is that escape speed from the Earth? Well, the energy is equal to this, right? And if the total energy, mechanical energy of a keys is negative, they're going to come back. It's bound to come back, right? So they're going to come back. So if I want that threshold speed that I need to throw it out so they never come back, I have to make the energy, well, at least 0. So you can just say, I'm going to just set this equal to 0, to solve the problem. Set this equal to 0, so it would be 1/2 mass of the keys, V squared, that's the escape speed, plus or minus minus, and then this is that, right? And then the mass of the Earth, mass of the keys, and I threw them from the surface of the Earth, which is, I'm at a distance from the center of mass of the Earth, which is equal to the radius of the Earth, right? And then that's equal to 0, and then this cancels that, and then V escape equals 2 capital G, mass of the Earth over the radius of the Earth, square root, and that's the escape speed from the Earth. By simply saying that the mechanical energy has to be equal to 0, that's like the threshold, then the keys are never going to come back. And for the case of the Earth, this turns out to be 7 miles per second. If I throw them 7 miles per second leaving my hand, and I neglect the effects of air friction, which will exist at that speed, maybe for a couple of seconds or 3, the keys are never going to come back. So if an electron is orbiting around the nucleus, a proton in a hydrogen atom, right? Or this is true of an electron, single electron, right? Just or one atom system orbiting around a heavy nucleus, then the energy will be negative if the electron goes around and around and around, because it's a balanced system. It has to be negative. It has to be negative. So if you consider the hydrogen atom, a typical question that you're asked is this. Okay, first of all, if you leave the hydrogen atom alone, you don't do anything to it. There it is, right? I mean, look at it. I don't know. I don't want to see it. I don't want to interact with it, right? Just an electron going around a proton, right? Which do you think of all of these energies is most likely going to be the energy of the electron as it orbits around the nucleus or the proton? Yeah. Leave nature alone, right? Things will find its way to minimize the energy. So the electron will be, leave it alone, is going to be here. So it's going to be, maybe this one works. Can I bring this one? All right, that's better. So the electron would be occupying that state. This is called a state, another state, another state. They're called quantum states. A state is just a particular situation that the system is in, right? So when you say, and there are names given to these different states. This is the lowest energy state. And we live on the ground of Earth, right? So we are at the ground level. So this is called the ground state. In Phys 185, you can talk about the frequencies of a string. What is the lowest frequency? Right? And it's called the fundamental frequency. So the fundamental frequency is like the ground state. Right? Now, what about this one? You can call this the second allowed state, or this is the first excited state. Second allowed, because this is allowed, that's the first allowed. This is the second state allowed, but this is the ground state, that's the lowest energy level, right? But if the electron is here, it is in the first excited state. In the music business, this would be in frequencies in terms of energy. Instead of energies, this would be the fundamental frequency, and then the next frequency that's allowed, right, is called the first overtone. Or the second harmonic if it's a string count at both ends, but is the second harmonic like the second allowed state, or the first overtone, the first tone above the fundamental tone. But it's called the first excited state. This energy level over here is called the second excited state. This is a building, and this is the ground floor of the building, street level. And this is, well, we call it the second floor, right? But you could call it the first floor above the ground floor. Excited above. Think of excited as above. This is like the second floor above the ground floor, right? We like to call it the third floor. It's the third allowed floor, kind of, right? And this is the third excited. So anyway, what if you find an electron going around a proton, right? The hydrogen atom, right? And it's going around it, so if you leave it alone, it'll be most likely in this state. Now, if I ask you the question, what is the minimum energy that I need to give that electron so that it breaks free of the proton? Sort of like the escape. In this case, it was the escape speed. There, you're not interested in the speed, you're interested in the energy that you would have to provide the atom so that the electron breaks free, divorces itself of the proton. What is the minimum energy? Well, if it's going to break free, the minimum energy is the one that will take the electron from this state to where? To freedom land. Freedom land is energy 0 or above. Everywhere up here is freedom land, but this is the threshold. So the minimum energy will be the energy that I would have to supply the atom so that the electron absorbs that energy and goes to that state where the energy is 0, so now it's free of the proton. It's not a bound system. So what will be that minimum energy? 13.6, because it already had minus 13.6 when it is in that state. If I give it 13.6, well, it takes in 13.6, it had minus 13.6, added them together, you get 0. So that's called this is the 13.6 electron volts, is also called the ionization energy of that state. Because ionizing the atom is like removing the electron from the atom, so that now you have an ionized system, a charged system. So what would be the ionization energy of that state? Of the first excited state, what is the ionization energy of that? 3.4 electron volts is the energy that will take it to freedom land. And what is the ionization energy of the second excited state? 1.51 electron volts, right? Now, what about above? Above, you have a continuum of states. These are not quantized. These are not quantized. These are just any value. If an electron is free, it can have any value of energy. Any value. So here you have a continuum. I'll write it over here. Here you have a continuum of states. And you have a free electron. In other words, unbound. Remember when we were talking about how X-rays are produced in a machine? And you emit X-rays from electrons from some metal, and they get accelerated through 100,000 volts or 80,000 volts, 35,000 volts, and boom, they collide with a target. Those electrons were free. Their energy is here. 10,000, 100,000 electron volts of energy. So those were free electrons. They were not bound, going around some nucleus. They were free. They were going from this this metal to that other metal. They're free electrons that can have any energy, right? That you accelerate them to. Alan, question?
So after the electron goes into like the free state, another electron will try to take its place in that.
If another electron comes by, yeah.
You have to consistently give it that 13.6 or more to keep it the hydrogen as it is by itself.
So if you have one proton and one electron going around it, right? Most likely, if you leave it alone, it'll be in this energy state, n equals 1, the ground state. And then if you shoot a beam of light, so that, actually that would be like ultraviolet. If you shoot a beam of ultraviolet light, a photon with this much energy, or more than that, then that electron that's going around the proton will absorb that energy and leave the proton. Now the proton is free, right? It's free. And if another electron comes into the vicinity, it can catch it, can make it go around it.
And to keep the hydrogen just as it is, you have to keep eliminating the electron.
I have to keep what?
You have to keep eliminating the first level. If an electron keeps coming in, you have to keep eliminating.
It depends on what you want to do, yeah. I mean, the electron could also be in this state and still go around the nucleus. The electron could be in this state and still go around the nucleus. It could be in that state and still go around the nucleus. What happens is that, suppose the electron is not there. Suppose the electron, maybe the atom, boom, got hit by something and the electron absorbed energy, and it was the right amount of energy that took it from here to there. Now you leave it alone, that electron is not going to stay there. Very soon, in fact, on the order of 10 nanoseconds, it's going to find its way back to the ground state. But as it jumps back, it'll emit there's going to be, when it goes from this energy level to this energy level, it lost energy. Yes. Because if you have minus 3.4 electron volts of energy, and then you have minus 13.6 electron volts of energy, you lost energy. How much energy did you lose? 10.2 electron volts of energy. That gets emitted as a photon.
Can you add 10 point, or can you take
So,
out 10.2 to get it to the second level?
no. If it's here, I need to give it 10.2 electron volts so that the electron has, it's like it owes minus 13.6 and you gave me 10.2. So now all that I owe is minus 3.4, so the electron will be in this level. So to make the electron go to, remember, this is going higher in energy. To make the electron go up this way, you have to give it energy. So it absorbs that energy. It's going to have more energy, so you have to give it energy. Now, if you leave it alone, the electron can jump back to this level, but as it does that, it's losing energy, and that energy gets emitted. So this is leading to the discussion of how atoms absorb and emit radiation, right? When you have an atom, like a hydrogen atom, and you have an electron in this state, right? If you give it energy, the atom will absorb the energy, and if it absorbs the energy, the electron is gonna jump either to this one, or that one, or that one, or one of these energy levels that's negative. If you give it, what if I have a hydrogen atom and I send in 15, a photon with 15 electron volts of energy? 15 electron volts of energy. What's gonna happen? It'll go from here to here. So what will be this energy then?
It'll be a free electron, or it'll be
1.4? 4. So what will happen is that the electron it's like the electron, right? Suppose you have this electron going around the nucleus, or going around the proton in the ground state. So its energy is minus 13.6 electron volts. And I give the electron 15 electron volts of energy. So it takes in the 15 electron volts of energy, it pays the proton 13.6 to get out, and walks away with 1.4 electron volts of energy. And that will appear as kinetic energy of the electron. Like someone is married and they want to get a divorce, and they say, okay, I'm gonna give you $13,600 for you to sign the divorce, but somebody gave me $15,000, so now you sign it, I divorce you, done, goodbye, and I walk away with $1,400. That's my kinetic energy. Sorry for the sad analogy, but you know. So, so let's consider some possibilities. Let's consider some possibilities. What if, consider, this is a hydrogen atom, plus, let's say this is the first orbit. I'll just do this to represent this second orbit, third orbit. So this is n equals 1, n equals 2, n equals 3. Even though if n is equal to 3, the electron could really be anywhere. But I'll just use this to make it easier. And the electron is here in the ground state. So what is the energy of that electron? Minus 13.6 electron volts. And what if I shoot a photon? I'm going to use gamma to represent that, and this one has 10 electron volts of energy. So I shoot this photon, and here we have a hydrogen atom. Clearly in the ground state. Will this hydrogen atom absorb this photon? And when it absorbs the photon, it's all or nothing. It's like, you know, there are some people that, you know, here's your food and you gotta eat all of it or don't touch it. So a photon is like, you take all of it or you don't take it.
Doesn't have enough energy to absorb it?
I don't know. I'm asking you.
No, I was saying it doesn't.
It doesn't. Well, why not?
Because it doesn't have enough energy to move the electron into the next.
Okay, so how do you know it doesn't have enough energy?
Because you would need 10.6 electron, or I mean 10.2 electron volt.
10.2? Okay, so think of it this way. That's correct. But think of it this way. This is a better way of thinking about it. What's the energy of the electron when it's interacting with that proton? It's minus 13.6 electron volts, right? If it takes that photon, if it absorbs the photon is gone, and it will take in 10 electron volts of energy, right? It took it. So what will be the energy? Minus 3.6, right? And then ask yourself the question, is that allowed? not allowed. So it won't take it. So the atom is gonna say, sorry, you don't have the right amount of energy. See you later, maybe next time, if you get more energy. Right? So what will happen is that you'll have the hydrogen atom like this. That's the nucleus. The electron will keep orbiting around n equals 1. And the photon will continue. In other words, the atom will be transparent to that photon. Goodbye. Yes? Let me change things a little bit. What if the photon coming in has an energy of 10.3 electron volts? And it interacts, I shoot it at this hydrogen atom in the ground state. So, forget about this, I don't want to, well, why not? What's going to happen? Will it take it or not take it?
No. It'll just pass right
Hmm?
I won't take it.
Why not?
Because it won't.
It's more than
Three.
10.2.
3.3 isn't an energy state. Or negative 3.3 electron volts isn't.
Okay, see, that's why I said that's the better way of thinking about it. So, if the electron takes that energy, it started with minus 13.6, right? And if it takes that energy of 10.2, 10.3, what will be the energy of it? If it takes it? It would be still negative. So it will still have to be going around the nucleus. But the restriction is that it has to be one of these. So the energy would be minus 3.3 electron volts. Is that allowed? It would take it from here to like over there, above that. But that's not allowed, it's gotta be minus 3.4. So it won't take it. So what's gonna happen is the atom is gonna say, sorry, goodbye. And the electron will keep orbiting around the ground state. Yes? If the energy is negative, right, if the electron is going to absorb it and still have a negative energy, it still then will continue to go around the nucleus, but therefore it is restricted by these values. It's got to be one of those, otherwise it won't take it. Yes? What if the energy of this incoming photon is, you want it to be 10.2? Or how about I ask you this, how much energy does this electron need to absorb to go to 1.51, minus 1.51? I guess it's better to put another zero here then. What should be the energy? So 13.6 minus 1.51. So that's 9. 1209? Did I do that right? So what if this photon comes in with an energy, gamma means photon, of 12.09 electron volts, and interacts with this hydrogen atom in the ground state? So what's going to happen? Will this hydrogen atom absorb that photon? So, well, the electron had minus 13 electron volts of energy, and then it just took in 12.09, plus because it absorbed it, minus because that was the energy initially, and this is 1, 5, and that's a 1, and that's a minus 151. So that's this one, right? Ooh. So what's gonna happen? The photon will be absorbed completely, right? So you're not gonna have a photon here, and you're not gonna have an electron there. You'll have an electron in n equals 3. Oh, maybe I'll draw a fourth one. Let's see. So now you have an excited hydrogen atom. And the energy will be E3, which is minus 1.51 electron volts. It will absorb it. So that atom will absorb that radiation. Yes? Now, what if I ask you, what's the wavelength of this radiation that will be absorbed by the hydrogen atom and bump the electron from the ground state to the second excited state?
10.2.
That's the energy. I want the wavelength. Right? So what would be the wavelength of this hydrogen atom, of this photon? What is the relationship between the energy of a photon and the wavelength of a photon? Well, Max Planck taught us that the energy of a photon is h times the frequency, Planck's constant times the frequency. The frequency of a wave is the speed of the wave divided by its wavelength. And I think I said it the other day, but I don't expect you to remember. Hc shows up a lot. And this is 1243, and this will be in nanometers times electron volts in these units. This is good to be familiar with because it cuts down on calculations. So then the energy of the photon is, what is it? 12.09, right? That's the energy of the photon, right? So this would be 12.09 electron volts. And now, if I use that for Hc in the numerator, it'll be 1243 nanometers electron volts, and then over lambda. And notice that the units of electron volts cancel, and I get the answer directly in nanometers. 1243 nanometers divided by 12.09. Now, how much is that?
102.
102? And do you know where in the electromagnetic spectrum this falls under?
Can it be infrared? Or no, wait, ultraviolet.
Ultraviolet, correct. Visible is from 700 nanometers to 400 nanometers. This is less than 400 nanometers, so that's the ultraviolet end. So if you send in a UV photon with this much energy, this atom will absorb it, and it will cause the electron to jump to the second excited state. Now, what if this just happened? So we just calculated what this wavelength would be, is 102. So what if this just happened? Right? And now we have an excited hydrogen atom. Okay? Can I erase this now? This is good to be familiar with. Can I erase this part of it? Now, let's consider this excited hydrogen atom. What's going to happen to it? So now we have a new problem. So we have an excited hydrogen atom. We have an atom where the electron is in the second excited state. N equals 3, right? What do you think is gonna happen? You don't do anything to it, just look at it and say, hey, do your thing. I wanna watch you do your thing. Come on, do it. Can't wait, I don't have all day. What do you think is gonna happen to that hydrogen atom? It's gonna, leave the system alone, and it'll look for ways to minimize its energy. So it's gonna find its way to the ground state. How could it do that?
By emitting a photon.
There are two possibilities, right? What is it?
Emitting a photon.
By going from where to where? So it can go from n equals 3 directly to n equals 1 and emit a photon, right? That's one possibility. Or, this is like driving from LA to Las Vegas after finals. Or it can decide to drive from LA or Orange County to Barstow, eat a sandwich, emit a photon, and then make another trip and emit another photon. So there are two possibilities. It can do it in one step, or it can do it in 2 steps. Yes? So what if this is an excited hydrogen atom, and the question is, consider this one, excited hydrogen atoms. In the n equals 3 state. What are the possible values of the wavelengths of the photons emitted that, let's say, it will emit, because it's there yet still? A lot of possibilities. So it's possible that it'll just emit one photon directly as it goes from this transition from n equals 3 to n equals 1, and emit one photon, or emit 2 photons by going from 3 to 2 and then 2 to 1. Right? So what are the possibilities? So one possibility, let's say n initial from 3 to n final to 1. That's just one photon. Right? And if you wanna sketch that, that would be like, what's up over here? That would be like this. You have a proton, n equals 1, n equals 2. I'll just start with n equals 3. It's initially like that, right? So it's here. I guess these are all electrons, right? In red. So that's the initial state. Now, what will you have if it makes this transition from 3 to 1? What will you have? You'll have then, after that transition, you have a proton. Now this is n equals 1, first orbit. That represents the first orbit. This represents the second orbit. And this represents the third orbit. But now, and this is after the emission, now the electron will be here. But this energy is not equal to this energy. So from conservation of energy, you have an emitted photon. Right? And the question is, what is that energy? Now, what's the energy of this atom over here? E initial is E3, which is minus 1.51. What about this one? That's in the ground state. E final for the atom is E1, which is minus 13.6. And then we have the energy of the photon. So if you use conservation of energy, E initial, that's what we have as the total energy before the emission, must equal the total energy after the emission, which is the final energy of the hydrogen atom, plus the energy of the emitted photon, right? And this will be minus 1.51 electron volts equals minus 13.6 electron volts plus the energy of the photon, right? And therefore, the energy of the photon is going to be 13.6 minus 1.51 is the 12.09, right? Now, the question was, what's the wavelength? Right? So we just set the energy of the photon equal to hc over lambda. So this would be 12.09 electron volts equals 1243 electron volts nanometers. So for lambda, right? So this cancels that, and lambda equals the 1.0, because we did this problem already, right? 102. That's one possibility. Now, let's look at this. This was, remember that this was, if it went from n equals 3 to n equals 1, from a higher energy level to a lower energy level, this is, emission of radiation by an atom. Now, what was this process here? This process was absorption of radiation by an atom. And I want you to notice something, because there's something that sometimes students get confused about. Right? I'm just using conservation of energy. What is the energy over here before the absorption? I have the energy of the photon plus the energy of the atom, right? So I have the energy of the photon plus the energy of the atom. That's like the initial energy of the atom, right? And that equals the final energy of the atom, because the photon got absorbed, right? So this is E final, it's E3, right? So this is E final. So notice that if you pay attention to this formula, right, the energy of the absorbed photon is E final minus E initial. But over here, the energy of the emitted photon, if I play with this is the emitted photon. For the emission, the energy of the emitted photon is E initial minus E final. Can you see the difference between this and this? In this one, the energy of the photon is final minus initial. Whereas here, it's initial minus final. It's reversed. Now, you don't want to deal with which one goes with what? Sketch it. This is the total energy before. That's the energy of the photon before it gets absorbed by the atom, and then it gets absorbed. So there's the photon. That's it. So the energy of the photon plus the initial energy of the atom is the final energy of the atom. If it's an emission process, the atom was initially excited, right? And then it is not excited, or it's at a lower energy level, plus the photon that it emitted. So in this case, the final energy plus the energy of the photon has to be equal to the initial energy. And then you'll never lose a minus sign. Yes? Now, there are two more possibilities over here, right? Instead of me doing that, you can do those other two possibilities, right? Just, it starts over here, and then first it's going to go from n equals 3 to n equals 2 and emit a photon. And then you can draw a new picture from n equals 2 to n equals 1 and emit another photon. Right? And you can find the wavelengths of those photons. And this is going to be kind of the spirit of the question in the final exam from this chapter, absorption, emission, and radiation. The comment that I want to make related to this topic, since I'm on it, really, is the following. Albert Einstein, in 1916, 1917, Albert Einstein said the following. He said, well, after the work by Ernest Rutherford, the positive charges at the center and the nucleus and the electron is outside. 2 years later, 1913, Niels Bohr comes along and he says the electron orbits around, right? And the atom can absorb radiation, can emit radiation. It can only emit radiation when it goes from one orbit to a lower energy orbit. Einstein said, right, in this case, there's a class next door. In this case, notice you had an atom that was initially in the ground state. You sent something to it, right? The atom absorbed it, a photon, and then it got excited. When you catch the atom in an excited state like this atom will find its way to the ground state. And like what we just described was that it's going to do that in either of two ways. It'll either find its way back to the ground state by having the electron undergo a quantum transition from n equals 3 directly to n equals 1 with the emission of a photon. Or it'll go to the ground state by first having the electron jump from the second excited state to the first excited state, emitting a photon, plus followed by another quantum jump of the electron from the first excited state to the ground state and emit another photon. And Einstein said in 1917, if the atom is left alone, right, it will emit a photon. Like this photon over here, right? The atom was left alone, just leave it alone. Do your thing, boom, it emits a photon. Einstein said there is no way to predict in which direction this photon is going to be emitted. Like, if this is the atom, it could emit that way, it could emit up, down, that way, at an angle, that way. There's no way to know a priori in which direction the atom is going to emit that radiation. And so this is called spontaneous emission of radiation. Because it did it spontaneously. It'll just emit it. And it turns out that, to go from the n equals 2 to the n equals 1 level for the hydrogen atom is like 10 nanoseconds, like 10 to the minus 8 seconds. It's ridiculously quickly. To you and I, it's like, who cares about that? 10 nanoseconds is like, so it's like, as you look away, by the time you look back, as quick as you try to be, the atom is already de-excited, it's already in the ground state, right? But nevertheless, it takes some time, right? Oh, okay, 10 nanoseconds or so. Okay, so Einstein said, okay, if you leave the atom alone and you let it emit spontaneously, it'll emit in some direction that we can't predict. It'll emit it. And it'll emit it within that time interval of 10 nanoseconds. We don't know if it's going to be in the beginning of the 10 nanoseconds, or like the first nanosecond, second nanosecond, third nanosecond, or at the end, but roughly it'll emit it within that time, but we don't know exactly when. And he came up with the following idea. He said, if, for example, so this is Einstein, 1917. He said, what if we know that this electron, for example, it doesn't apply to this particular system, but because of the numbers that I'm going to use, but if we catch this electron in an excited state for the atom, right? See, the energy difference between these levels is never the same. There are no two energy levels where this energy difference is the same as this energy difference. They're just different. Or between this and that. Because of that 1 over n squared, it screws up the symmetry. So they're never equally spaced in energy. So if, for example, you catch, let me just do this, like you have, let's say, a nucleus, and you have n equals 1, n equals 2, n equals 3, I mean, you know, n equals 4, just to give an example, right? Suppose the electron is here. Right? It's excited, let's say it's excited, right? Now, suppose the electron wants to go to n equals 2, so there's an energy difference over here of delta E. Whatever that is depends on the atom and so on, right? Some energy difference, right? Delta E. If, right, so this electron, if you leave it alone, it's gonna go, let's say here, and emit a photon in some direction that you don't know, or can't predict. So Einstein said this, what if you send in, what if you catch it? Catch this atom in an excited state. And you send in a photon towards this atom, and the energy of this photon happens to be exactly that difference. Now, first of all, this difference corresponds to the energy difference between these two levels, right? If the electron is here, that's the lower energy level, it will absorb it and go here. But this electron is already here. It cannot absorb that, because in order to absorb that, it would have to go to another state where the energy difference between that state and the higher energy state would be that, but they're never the same. So there's not going to be another state that will have the same energy difference as these two. So, yes, you realize the problem? It's already excited. If the electron were here, it would absorb that photon and jump to there, and the photon is gone. Right? But remember, the energy differences are never the same, never the same. So, but what happens is that this electron is already in an excited state, right? So if it were to absorb this, it would have to go from here to another level, but then this energy difference would have to be the same as that, which is not, because they're never the same. So Einstein said, if you catch the atom in an excited state, and you send it this energy in a photon, and the energy of the photon would be the one that caused it to get excited from this state to that one, but it's already excited, so it's not going to absorb it, then what will happen is that this atom can interact with this photon, and essentially it's like this photon will talk to the atom and say, emit now. It'll stimulate it to emit. So what will happen is that now you're going to have n equals 1, n equals 2, n equals 3, n equals 4, and now this electron will be convinced to go there to n equals 2. But this photon was not absorbed. Yes? It would have been absorbed if the electron were there. Then it will take the energy and then jump up here, but it's already there, so in order to absorb it, it would have to go to another level which would have the same energy difference, but that doesn't exist. So what will happen is that this electron will be convinced by this photon to go there. This photon would not be absorbed, so that photon would continue. It just talked to the electron, and it would continue like that. Well, the energy of the photon would be that. But then, what happens when this electron jumps from here to there? It emits a photon, right? And Einstein said it should emit a photon in the same direction that this one was traveling, as opposed to randomly. Like over there, you don't know which way it's going to be emitted. So if I send this photon to the right, this atom will emit to the right. If I send this photon up, this atom will emit up, and not only in the same direction, but also in phase with it, to give you constructive interference. So the energy of this was the incoming photon, the stimulating photon, this is the emitted photon, the same energy. Now, how many photons did you have in the beginning? You had 1 photon. And how many photons do you have in the end? 2 photons. So this is, and the photon is like light, so this is light. amplification. Because you had a photon and then you got two photons. But what was the process? This was emission of radiation, but it wasn't spontaneously. This atom was induced, right? It was stimulated to emit the radiation by this incoming photon. So this is really stimulated emission of radiation. And it's not going to do it like later. As soon as that atom comes in, that's when this guy is going to emit. So you have control over when the atom emits. And so this is light getting amplified because you got two photons instead of just one. And what was the process? Stimulated emission of radiation. 1917. And if you look at the first letters, it's a laser. So Albert Einstein laid the foundation, the theoretical foundation for the creation of this technology of lasers. The first laser was built in 1960 by Mayman here in California. Einstein died in 1955. So he could have won a Nobel Prize for this. But the first laser was built out after he died. So he didn't win a Nobel Prize. It was given to other people, but not to him because he was dead already. So in a laser system, what's done is this. You have a medium. It's called the lasing medium. And the medium could be a solid, like, crystal, like the YAG laser, the laser pointer's got some semiconductor in there. It could be a liquid. It's called a dye laser. It's just a liquid. It's made up of some molecules that are carcinogenic. You have to be really, really careful when working with those lasers. I used to work with one of them, and we had to change that liquid every couple of months, and we have to wear special gloves, and there was a pump. So anyway, you wouldn't drink that thing if you got thirsty. And then it could be a gas, like the helium neon laser, the argon ion laser. We had argon ion lasers in there. And what you do is, this, whatever, it's a solid, liquid, or gas, you have atoms in there, right, making up the medium. And what you need to do is excite them. As an excitation, you could use a lamp. And the YAG laser, we used a lamp that flashes. And you had like an elliptical cavity, and at one focus, there was a rod with a YAG rod. YAG means yttrium aluminum garnet, doped with neodymium. And then at the other one, you had the lamp at the other focus. And that way, when the lamp, emitted light, it would hit this and it would always go there. So you concentrate excitation on the crystal and that get it excited. So now you have excited atoms, and maybe one atom will emit radiation this way, it will be lost. Another one would emit radiation this way, it will be lost. But some of those would emit radiation towards this mirror here. So this is called the reflecting mirror. And the light would come in, and you make it 100% reflecting. And what happens is going to hit, and what happens when that photon goes back? If you keep exciting, then as this photon comes in, it'll encounter excited atoms. And it'll stimulate atoms to emit in this direction. So if you have one atom over here, right, and this photon comes in this way, and this photon goes that way, it'll stimulate it to emit in that direction. And then now those two photons can stimulate two more excited atoms to emit in the same direction. Then you have 4, and then you have 8, and so on. This happens with all of these, and you get a lot of photons over here, and then you put another mirror over here, 95% reflecting. It's called the output copper. So 95% reflecting. So 95% of the energy goes back. What about the 5% of energy that goes through? That's your laser output. So you could use a lamp to excite the medium, so that the atoms get caught in an excited state so that they can be stimulated to emit radiation. In the helium neon laser, we have some helium neon lasers, you just pass an electric current through the helium neon gas. The argon ion laser, just an electric current through the gas to excite the atoms. In that case, instead of sending in a photon to excite the atoms, you send in a beam of free electrons from here, and they're just coming in and boom, 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 hit the atoms, excite them, and then when they go back to their ground states, they emit the radiation. Some of them will go directly towards the mirrors, and then that, gives you gain, and then you can have a laser output. So you can use an electron beam to excite the atoms. I used to work with a laser. The YAG laser, emits pulses, and we used to focus it on the dye laser, the one with the liquid. So we used the laser focused on a medium to make that medium lace, and then we would get shorter duration laser pulses. In the titanium sapphire laser, same thing. The output of an argon ion laser is focused onto the titanium sapphire crystal, and it would be made to lace. So you could use a lamp, an electric current, or a beam of electrons, so an electric current, or another laser to make a laser run. So there are hundreds of different lacing materials, different wavelengths, and but nowadays, lasers are used, supermarket scanners, right? They're used in eye surgery, they're used for, arthroscopic surgeries, in the medical field they're used very widely, weapon system, and, they're just used all over the place. So if he had lived a little longer, probably would have won a Nobel Prize for that work.
So why do we want to reflect the 95%?
So you need that energy to keep going back and forth and to keep exciting these guys so that they keep emitting.
And that they're all in the same phase.
Huh?
They're all in the same phase.
And they're all in the same phase. So the laser output, one thing that's good about it is that it's very collimated and it's very coherent also. It's like you get constructive interference. And so you can get a big pulse. Well, in my case, it was more exciting to emit pulses of light. And the time separation between the pulses as they come out is the time that it takes a photon to go to the other end and come back. It goes out and then comes back, goes out.
Fancy of like a stable light.
Because, if you have pulses of laser light coming in like this, so like for my work, for my thesis, we consider a thin film of gold, and we would focus a laser pulse on the front surface and it will reflect. So you would send in these pulses of light, and then you would excite electrons over here. Guess what happens to those electrons? So you have a high concentration of excited electrons here and none over there. They went to the other end. So then the electrons would go this way, and as they arrive over here, they'll change the reflectivity of that surface, and then we would come in with a low intensity laser pulse in the back to measure the change in the reflectivity over there, to measure or detect the arrival of the electrons at the other end. But then, there's a lot more to it. For one thing, there was a group of Russians in the 1950s. They wrote a theory that said that you can think of a metal as a two-step